Okay, let's talk about probabilities of combined events. So, just to illustrate, let's think of poker. Here you see what's called a royal flush. So, we've got 10, Jack, Queen, King, and Ace all in suit heart. And the idea is, can we determine the probability of this royal flush by kind of putting it together? What are the chances of a flush? So everything's kind of in suit heart, and the probability of a straight, which means 10, Jack, Queen, King, Ace in any color, in any suit. Those of you who play cards, probably to you that means a bit more. In general, we're gonna use a bit of gambling lingo and some things about poker and roulette and all those things, because they're like brilliant examples for probabilities. So how do we put things together for that? So conditional probabilities. There's now a new symbol, this one here, which means the probability of A under the condition that B is true. So what we're interested in is the first thing here before the line, the A. We want to know how likely is A, but there's already some prior knowledge, and that is the B. This is a very important concept, and let's look at it in sort of this tree diagram that I've got below. And to make it a bit more approachable, less dry, let's assume A means there's sunshine and B means it's the weekend. So at first we start here. There's a probability for weekend, and that is probably something like 2/7 if you say like all days are quite likely. Yeah, you've slept for a week and you wake up, and what's the chance? What are the chances it's weekend? Obviously, the probability that it's a work day is 5/7. Yeah, so those two, P of B plus P of not B, add up to 1. Yeah, that's how these diagrams work. And then we could be very lucky. So let's follow the top branch. So it is weekend, we're here, B is true, and we could have sunshine. So again, top branch, we're here, sunshine and weekend. So the probability we get here is the probability of, sun plus weekend. That is the best. That is what we want. Okay. Obviously, there's also the chance that we got a weekend and no sunshine. Yeah, that's this one here. So that's weekend and no sun. Yeah, that would be sad. Okay, now we know the endpoints here. They're kind of the combined events, sun and weekend, or no sun and weekend, or like all the others, no sun, no weekend, all the 4 combinations. Oh, by the way, those 4, they also add up to 1. Yeah, that's basically the whole sample space that we see here. But what we left out now is what is this bit here in the middle? How do we get from here to here? And this bit is where the conditional probabilities come into place. Let's take this off for a moment. So, what are the chances if you already know it's a weekend? Yeah, we've looked at our watch, weekend, Saturday morning. What are the chances for sunshine? Then there's a certain probability for sunshine, P of A, but we already know it is a weekend day. And if you'd be a pessimist, you'd say if sunshine normally is like 50-50, but on a weekend chances are definitely slimmer. So we've only got like 40% chance of sunshine on a weekend. Okay, because yeah, that's Murphy's law. So let's quote Murphy here. Obviously the chances then, branches always have to add up. So the chances that we get no sunshine on a weekend, so P of not A, given that it's the weekend, have to be 60%. Yeah, those two, this one plus this one, have to add up to 100% as well. And it's basically the conditional probability just brings us from, in this branch, from one joint, from one point here to the next one. So we already know that B is given. It only takes us to the next one. Same down here. So here, just like show you the difference. P of not B in a working day. What are the chances? This is like sunshine, sun on working day. Obviously, if you already know it's a working day, chances for sunshine are a lot bigger. Let's say that's a 70% chance for sunshine, and then obviously no sunshine is less likely. Okay, those two also like have to add up to 1. Just resist the temptation to combine those two. So this one here, the 40% and the 70% here, they add up to 110%. What? No, obviously that doesn't make any sense, and yeah, we can't really add them up. They're conditional probabilities. They only work on the basis that we are at a certain spot already. That's like our precondition, and that can't change. So those two don't have any meaning combined. Yeah, we can combine either those ones here or the individual branches here, those two, they add up, or those two. Right, so let's do some arithmetic with those conditional probabilities. One obvious one is the probability of not B is 1 minus B. If B has a 70% chance, then probability of not B is 30%. Yeah, pretty obvious. This one is also fairly obvious. So if you have a combined event with a union, probability of A or B, or A union B. Yeah, there's also like the or event. Obviously we can think about it as the probability of A plus the probability of B. But if you look at it in a sort of a Venn diagram style, if this is event A and this is event B, and then you've got a probability for A, so you're taking all that and then you're adding the probability for B, which is all that. Then we've taken this little bit here double, so we need to take off the intersection because that has been accounted twice for. So fairly plausible formula. The one that we just had is this one. So the probability of A and B, or A intersection B, is probability of B times probability of A, given that B is true. You can also see it the other way around. So this is kind of symmetrical. You can also say I want to have the A here as a condition, so it could be probability of B under the condition that A is true times the probability of A. If we take this formula and spin it around a little bit, we end up with Bayes' rule. So basically all I'm doing is I solve this bit here for that first term, and yeah, outcomes Bayes' rule. Interesting is, like here I've got A under the condition B, and we can swap the order to B under the condition that A is true. That is very powerful. We'll see in a moment when we look at examples how we can use this and how it gives us some great insights. Apart from that, if A and B are independent, then obviously the whole thing simplifies. So probability of A intersection B is just the product. We'll often use that for some experiments where we roll the dice twice or something like that, assuming the first run didn't affect the second one, so they are independent. So rolling 2 6s in a row is like 1/6 times 1/6. Yeah, it would be this product here, assuming they're independent. Obviously, if they're not, so if the die changes, if we roll a 6, it likes to stick on that side again, then we have to work with a rule from above and introduce conditional probabilities. But yeah, often it's very useful to have the independence and simplify things. Okay, let's look at, so that's all probably a little bit confusing. Let's look at some real numbers in an example. So we've got a random number generator, and it gives us a number between 1 and 20. Any number, they all have the same probability. So the probability of an odd number is 10/20. It could be a 1, a 3, a 5, a 7, and so on, up to 19. So half the numbers between 1 and 20 are odd numbers, so 50%. We can also look at the probability of a prime number. You've already heard about prime numbers, I guess, in school. So prime numbers can only be divided by 1 in themselves without a rest. So these are the prime numbers between 1 and 20, 2, 3, 5, 7, 11, 13, 17, 19. So there's 8 of them. So the probability of obtaining a prime number is 40%, 8 out of 20. And now we can ask, what is the probability of an even prime number? And looking at the prime numbers here, you will see they're all odd, because obviously, yeah, all even numbers can be divided by 2, which then makes them not prime. The only exception is 2 itself. That is also considered a prime number. So there's one single number that is even and prime. So the answer has to be 1 over 20. But we wanted to think of it in an additional way. We want to think of it as a combined probability with the formulas from before. So we can say the fact that it's even and it's prime, we can use Bayes' rule and we can expand it. So we can say, okay, that means it's even under the condition that it's prime. So now we need to look here. If we know it's a prime number, it has to be one of those 8. Okay? So the odd one, the even one in those 8 is the 2. So the probability of this is 1 in 8. Yeah? And then we gotta multiply this with the probability of just a pure prime number. So we've calculated it before. It's like 8 over 20, 40%. We multiply, and obviously out comes 5%, yeah, which is exactly 1 over 20. 1 in those 20 numbers is even and prime. So it comes out right. Cool. Let's do some exercises with this, and to make it a bit fun and interesting, we're gonna play with a deck of cards. Just for those of you who haven't played cards, like a standard deck of 52 looks like that. You've got 4 different suits. So these are the 4 suits. There's clubs at the bottom, then diamonds, then hearts, and then spades at the top. And then you've got the different numbers on them. It's you basically got an ace, then the numbers from 2, 3, 4, 5, 6, 7, 8, 9, 10. Those numbers, and then there's a jack, a queen, and a king. Okay, so there is basically 13 of those. It doesn't really matter like what they're called. Main thing is you can always look up what cards there are in the game, and I'll ask you little questions about it. So let's have a go. What is the probability of getting hearts or a king when you pick one random number from this complete deck of 52? Perfect, yeah. 16 over 52. We could count. I mean, what we could do is like go above and say, okay, we've got 4 kings, and we've got the hearts, and now let's count, and it's gonna be, it ought to be 16. But if you don't want to do this like that, how do we calculate? So we know hearts, this means hearts or king. I use Bayes' rule, or the expansion rule from above. So probability of hearts, and every 1 in 4 cards is a heart. There's like only 4 suits, so this is 1/4. Kings, there's 13 different types of cards, and king is one type, so that's 1/13. And then there's only one king of hearts in there, so there's 1/52. That's how we add up the numbers, and out comes 16/52. And if you've counted above in our deck with a yellow just marked, it comes out right. Okay, second example. What is the probability of 2 hearts when picking 2 cards from the complete deck? Exactly this one here. Again, we can use the rule heart 1 intersection heart 2, so we have an AND. There's the AND intersection corresponds to an AND. We can write it like this, and the probability of the first heart is easy. It's like 1/4 or 13/52. Then the probability that we get a second heart when we've already had one, that changes when we've already had one heart, because now there's only 51 cards in the deck, and there's only 12 hearts left because we have already chosen one. So this is the second factor, and then it adds up to almost 6%. Excellent, well done. So let's look at a even tougher example. This one uses Bayes' rule, and it's quite interesting one. So Dr. J is a terrible doctor, and the chance of getting a correct diagnosis with him is only 40%. So A is the correct diagnosis. If he gets the diagnosis right, then you've got quite good chances. Then your chance of dying, so D is for dying, is only 20%. But if he gets it wrong, then it looks bad for you. Then you're up at 50%. So quite tough times. So first of all, what is the probability of a wrong diagnosis? That one should be easy. But very interesting is, what is a patient's a priori chance of dying when you see Dr. J? All we know is like the conditional probabilities depending on his diagnosis, but what is the pure one a priori? And there's a little hint. Okay, let's talk about the first one first. The wrong diagnosis is easy. That's 1 minus the right diagnosis, so 60%. Wrong diagnosis, 60%. Now, how do we calculate the second one? With this hint, we can do the following. So the chance of death is, we can say, is like you could die with a correct diagnosis or with a wrong diagnosis. Yeah, 2 possibilities, and that adds up to all of sample space. Yeah, this one here is omega, so I can just distribute it out. Just a little trick. And then obviously the chances of dying is probability of dying with a correct diagnosis plus probability of dying with a false one, and then those ones I can expand into the Bayes rule, and those are the ones that have been given here in this example, and we can put the numbers in. So a priori, before you've seen Dr. J, you've got a 38% chance that things are turning for the worse. And then, yeah, if you're lucky, if he's giving you a correct diagnosis, it lifts to 20%, or if he's giving you a bad one, then yeah, it becomes worse to 50. Cool. So just using Bayes' rule, we can find out interesting things that are not easily accessible otherwise. Great, excellent. So using all this, we're gonna take another step. Now we wanna go into combinatorics, and I'll tell you all about it in a minute.